Imagine outdoor air at 95 degrees Fahrenheit on a summer afternoon, entering a pipe buried 8 feet underground, traveling 100 feet through the stable 55-degree ground temperature, and emerging at the other end, cooled to 62 degrees, without any compressor, refrigerant, or electricity beyond a small fan. In winter, the same system takes 15-degree outdoor air and delivers it to the home at 45 degrees, providing substantial preheating that dramatically reduces heating energy requirements. This is earth tube ventilation, a technology used in Chinese rural construction for millennia, refined through European innovation in the 1970s and 1980s, and deployed in contemporary high-performance construction across climates worldwide. The approach exploits the stable underground temperatures that remain around 50 to 60 degrees Fahrenheit year-round in most regions, using buried pipe systems to precondition ventilation air before it enters buildings. The resulting temperature moderation provides free cooling in summer and free heating in winter while meeting code-required ventilation needs. Understanding how earth tubes work, what their construction requires, and where the approach fits. Contemporary building helps explain why a growing community of high-performance builders considers this technology an important complement to conventional HVAC approaches for buildings pursuing maximum energy efficiency. The fundamental physics of earth tube performance exploits the thermal stability of soil at depths below frost penetration. Soil temperatures at depths of 6 to 10 feet remain remarkably stable throughout the year, typically matching annual average outdoor air temperatures for the specific location. Temperatures in temperate regions typically stabilize at 50 to 60 degrees Fahrenheit, warmer than winter air and cooler than summer air. Outdoor ventilation air drawn through pipes buried at these depths exchanges heat with the surrounding soil, moderating the air temperature towards soil temperature as it travels through the pipe system. The resulting conditioned air provides free cooling and heating relative to outdoor conditions while meeting ventilation requirements. The sizing and configuration of effective earth tube systems depend on specific performance objectives and site conditions. Typical residential installations use 4 to 12-inch diameter pipes, 50 to 200 feet in length, buried 6 to 10 feet deep in appropriate soil. The pipe material must resist corrosion and soil chemistry while providing adequate heat transfer to ambient soil. HDPE plastic pipe has emerged as the preferred contemporary choice for most applications, though concrete, clay, and metal alternatives have been used historically. The system sizing matches ventilation requirements and performance objectives, with larger systems providing more substantial conditioning at higher installation costs. The historical development of earth tube concepts traces through multiple traditions spanning continents and millennia. Chinese rural construction has used earth-cooled tubes for summer cooling since at least the Han Dynasty over 2,000 years ago. Persian wind catchers combined with underground channels provided similar cooling in arid regions. Contemporary European research during 1970s and 1980s refined modern applications for both residential and commercial buildings. Institutional research at technical universities across Germany, Switzerland, and Austria documented performance and refined design approaches. The accumulated knowledge supports contemporary applications in diverse climate contexts across residential, commercial, and institutional building types. Dr. Hartmut Reinhard Schmidt, a German building physicist who has designed and monitored earth tube installations for over 30 years, has documented consistent performance across diverse building types and climate conditions. His measurements show typical residential installations delivering 25 to 45% reductions in ventilation-related heating and cooling loads, with larger commercial installations achieving similar or better percentage savings at larger absolute scales. The performance documentation provides technical foundations supporting continued adoption of the approach in contexts where installation conditions are favorable. The soil conditions affecting earth tube performance include thermal conductivity, moisture content, density, and stability across seasonal variations. Moist clay soils typically provide excellent thermal conductivity that produces strong heat transfer between pipe air and surrounding soil. Dry, sandy soils provide poorer thermal conductivity that reduces temperature moderation. Groundwater presence affects both thermal performance and installation feasibility. Proper site assessment includes soil analysis that determines whether earth tube installation will produce expected benefits or face performance challenges from unsuitable conditions. Ylva Bergström Nilsson, a Swedish building integration specialist who has coordinated earth tube installations with other building systems across multiple passive house projects, has documented how earth tubes integrate optimally with heat recovery ventilation systems to produce superior overall ventilation performance. Her installations combine earth tube preconditioning of ventilation air with heat recovery between outgoing and incoming air streams, capturing both earth temperature benefits and heat recovery benefits in coordinated systems. The integrated approach produces substantially better ventilation performance than either technology alone, supporting application in passive house and similar high-performance building contexts where maximum efficiency matters. The installation process for earth tubes requires substantial site excavation and careful attention to grading, drainage, and connection details. Trenches 6 to 10 feet deep and 100+ feet long require substantial excavation equipment and labor. The pipe runs must maintain consistent slope to prevent water accumulation within the pipes. Entry and exit points require connection details that prevent water infiltration and support fan connection for active ventilation. The installation complexity exceeds what typical DIY builders undertake without professional equipment and expertise, though motivated owner builders with access to appropriate equipment can successfully complete installations. Now for the obstacles and limitations that affect earth tube adoption. First, the installation costs are substantial compared to conventional ventilation approaches. Earth tube installations typically cost $3,000 to $10,000 depending on length, depth, and site conditions. The costs exceed conventional mechanical ventilation equipment, even when conventional equipment is substantially more sophisticated. The cost premium is highest during initial installation, with continued operation essentially free, producing favorable long-term economics but demanding substantial upfront investment that not all projects can accommodate. Second, the site conditions requirements restrict applicable projects to those with adequate land area for pipe runs. Dense urban sites typically cannot accommodate earth tube installations due to property size limitations. Sites with unsuitable soil conditions, including rocky ground, high water tables, or contaminated soils, may face practical installation challenges. Sites with existing underground utilities require careful coordination to avoid conflicts during installation. Third, the moisture and microbial concerns that earth tube applications could create require attention during design and operation. Humid pipe interiors could potentially support microbial growth that would degrade ventilation air quality. Proper design, including adequate drainage, antimicrobial interior surfaces, and periodic cleaning provisions, addresses these concerns effectively. Improper design or neglected maintenance could create air quality problems rather than improvements. Fourth, the climate limitations restrict benefits in very mild climates where outdoor temperatures are close to soil temperatures throughout the year. The temperature moderation benefits matter most in regions with substantial temperature differences between outdoor air and soil temperatures. Very mild climate regions may achieve limited benefits that don't justify installation costs. Climate-specific analysis appropriately guides adoption decisions rather than universal recommendation regardless of conditions. Fifth, the maintenance accessibility concerns affect long-term serviceability. Once installed underground, earth tube systems are difficult to access for inspection, cleaning, or repair. thoughtful design includes provisions for cleaning and inspection while accepting that detailed underground pipe maintenance is impractical compared to above-ground mechanical systems. The maintenance limitations require accepting that earth tube installations represent essentially permanent infrastructure with limited intervention possibilities after installation. Despite these considerations, earth tubes represent remarkable passive conditioning technology that delivers substantial benefits for appropriate applications in suitable site conditions. The energy savings from earth tube installations accumulate substantially across building lifespans. Typical residential installations reduce heating and cooling energy by 15 to 30% through ventilation load reductions, producing annual savings of $200 to $600 depending on climate, building size, and fuel costs. Continued savings across 50-plus year effective operational lifespans accumulate to $10,000 to $30,000 in operating cost reductions over full system lifespans. The long-term economic returns justify the substantial initial investments in appropriate applications. Chidinma Okonkwo Eze, a Nigerian building design engineer working on African tropical construction, has documented how earth tube applications in African contexts face different optimization priorities than temperate applications. Her research examines how earth tubes can provide cooling benefits in tropical contexts where cooling is the primary concern rather than heating, with design approaches emphasizing maximum summer cooling performance over seasonal balance. The tropical adaptations demonstrate how universal principles translate to specific climate contexts through appropriate design customization. The integration of earth tubes with passive house construction and similar high-performance approaches produces systems delivering remarkable overall performance. Passive house standards require continuous mechanical ventilation that earth tubes can provide more efficiently than conventional mechanical systems alone. The combined earth tube and heat recovery ventilation systems reduce ventilation-related energy consumption by 50 to 75% compared to conventional code minimum approaches. The integrated systems support passive house performance targets in climates where conventional approaches would face greater challenges. The commercial applications of earth tubes include office buildings, schools, and various institutional facilities. Larger earth tube systems scaled to commercial ventilation requirements produce similar percentage savings to residential installations at substantially larger absolute scales. Commercial projects with adequate site conditions and long-term ownership horizons often achieve favorable payback periods through substantial energy cost reductions across the large ventilation volumes that commercial buildings require. Several demonstration projects have documented commercial earth tube performance across extended operational periods, supporting continued expansion of the approach beyond residential applications. Prakash Bhattacharya Roy, an Indian architect designing institutional and commercial buildings across South Asia, has documented how earth tube applications in Indian commercial buildings produce particularly favorable economics due to the combination of substantial cooling loads and relatively low installation labor costs. His projects demonstrate that contemporary institutional construction in appropriate climates can achieve dramatic energy performance improvements through earth tube integration at cost premiums that conventional economic analysis readily justifies. The Indian commercial experience provides evidence for expanding applications in similar tropical and subtropical contexts. The comfort improvements from earth tube conditioning extend beyond raw energy savings to affect perceived comfort in ways that basic performance specifications often overlook. The gentle air conditioning that earth tubes provide differs qualitatively from conventional air conditioning, producing more stable conditions without the dramatic temperature swings that conventional systems often create. Occupants consistently describe earth tube-conditioned spaces as more comfortable than conventionally air-conditioned spaces, with qualities including absence of cold drafts, consistent temperatures across spaces, and quieter operation, all contributing to the preference. The humidity control characteristics of earth tube systems require attention because performance differs substantially between heating and cooling seasons. During cooling seasons, earth tubes can produce condensation as warm, humid outdoor air cools against cool pipe surfaces, requiring drainage provisions to manage the condensate. During heating seasons, the cool supply air may require humidity addition to maintain comfortable indoor humidity levels. The humidity considerations require system design integration, but don't create insurmountable obstacles to effective application. Mireia Domènech Puig, a Spanish architect who has designed earth tube integration for Mediterranean climate applications, has documented how the approach performs optimally for providing summer cooling and modest winter heating in Mediterranean climates where seasonal temperature differences are less extreme than continental climates. Her projects across Catalonia and Valencia demonstrate that Mediterranean applications achieve good benefits through simpler systems than continental applications typically require, with installation costs proportionally lower than continental projects while still producing meaningful comfort and energy benefits. The regional adaptation supports climate-appropriate design decisions. The research continuing on earth tube technology focuses on performance optimization, microbial control, and integration with broader building systems. Computer modeling tools enable detailed performance prediction before installation. Microbial studies document air quality implications and identify design factors supporting good air quality. Integration research examines how earth tubes coordinate optimally with HVAC systems, heat recovery ventilators, and building automation. The continued research supports refinement of best practices and expanded confident application across diverse contexts. The educational resources supporting earth tube adoption have matured through decades of practitioner experience and academic research. Published technical guides provide design information for interested practitioners. Workshops through sustainable building schools teach practical installation approaches. Manufacturer resources support product selection and specification. Professional consulting services provide site-specific design expertise. The educational infrastructure supports motivated builders and homeowners pursuing earth tube installations despite the technology's unfamiliar appearance to conventional construction audiences. The depth considerations for earth tube installations involve practical trade-offs between performance and installation costs. Deeper installations reach more stable soil temperatures, providing better performance, but require substantially more excavation effort and cost. Typical residential installations reaching 6 to 8 feet deep capture most of the available performance benefits at moderate installation costs, with deeper installations providing diminishing returns for most applications. Commercial installations sometimes reach 12 to 15 feet deep, where substantial ventilation volumes justify the additional excavation costs through proportionally greater performance benefits. The depth optimization requires analysis of specific project economics and site conditions rather than universal specification applying to all contexts. Rodrigo Castillo Mendez, a Guatemalan-American geotechnical engineer who has consulted on earth tube installations across Central America, has documented how volcanic soil conditions in his region produce both advantages and challenges for earth tube applications. The excellent thermal properties of volcanic soils produce strong heat transfer performance, while the sometimes unstable volcanic terrain creates installation complications that careful site investigation must address. The regional experience demonstrates how universal principles interact with specific local conditions in ways that generic design guidance may not adequately address. supporting site-specific analysis for projects in unusual geological contexts. The automation and control considerations for earth tube systems in contemporary buildings determine whether installations achieve available benefits through intelligent operation. Fan controls that respond to conditions inside pipes, outdoor temperatures, and indoor air quality produce better performance than simple continuous operation. Dampers that allow bypass of earth tubes during favorable outdoor conditions prevent unnecessary fan energy consumption when earth tube conditioning isn't beneficial. Integration with building automation systems coordinates earth tube operation with other HVAC functions for optimal combined system performance. The automation sophistication has improved substantially with contemporary building automation platforms, enabling better performance than earlier installations achieved with simpler control approaches. The material innovations improving contemporary earth tube performance include specialized pipe products designed specifically for earth tube applications rather than repurposed general-use piping. Antimicrobial interior coatings address microbial growth concerns through integrated material design rather than relying purely on operational measures. Smooth interior surfaces reduce friction losses that affect fan energy consumption. Reinforced wall sections provide durability in challenging soil conditions while maintaining adequate heat transfer characteristics. The specialized products cost modestly more than general-purpose alternatives, but produce better long-term performance with reduced complications. Contemporary high-performance earth tube installations increasingly specify these purpose-designed products rather than adapting general-purpose piping to earth tube use. Margit Waldvogel-Sommer, a Swiss building system specialist who has designed earth tube systems integrated with geothermal heat pump systems, has developed combined systems that coordinate passive earth tube conditioning with active geothermal heating and cooling. Her projects demonstrate that the same excavation can support both systems, sharing installation costs, while capturing synergies between the passive ventilation preconditioning and active thermal conditioning. The integrated approach produces total system performance substantially exceeding what separately installed systems would achieve while reducing total project costs through shared excavation and trenching work. The system integration demonstrates emerging sophistication in contemporary high-performance building design. The climate change considerations for earth tube applications deserve attention as climate patterns shift across regions. Warming climate trends affect soil temperatures at earth tube operational depths, though the changes proceed slowly enough that installations designed for current conditions will generally remain effective across their operational lifespans. Changing precipitation patterns affect groundwater levels and soil moisture that influence earth tube performance. Climate adaptation considerations increasingly appear in design discussions, though the substantial thermal inertia of soil at depth provides substantial buffering against short-term climate variations. The air quality monitoring research around earth tube installations has generally supported their application while identifying specific design considerations that affect outcomes. Long-term monitoring studies in European installations show that properly designed systems, with appropriate drainage, material selection, and periodic maintenance, produce air quality comparable to or better than conventional outdoor air after filtration. Poorly designed systems with inadequate drainage or unsuitable materials can create air quality problems. The monitoring findings support adoption of best practice design approaches while identifying the specific factors that separate successful installations from problematic ones. Design guidance incorporating these findings enables reliable application without unacceptable air quality risks. The comparative analysis of earth tubes against alternative air conditioning approaches shows different advantages in different contexts. Compared to conventional air conditioning, earth tubes provide lower operating costs but cannot meet all cooling demand in hot climates. Compared to heat recovery ventilation alone, earth tubes add preconditioning benefits but at higher installation costs. Compared to geothermal heat pumps, earth tubes provide passive operation without the mechanical complexity that heat pumps require. The optimal choice among these alternatives depends on specific project priorities, site conditions, and budget considerations rather than universal superiority of any single approach. Many high-performance buildings actually use multiple approaches in coordinated systems rather than selecting exclusively among them. The code and regulatory treatment of earth tubes varies substantially across jurisdictions. Some European countries have developed specific code provisions addressing earth tube design, installation, and operational requirements. North American codes generally lack specific earth tube provisions, but typically accept installations that meet general mechanical ventilation requirements through alternative methods documentation. The regulatory treatment affects project feasibility and costs, with regions having established code frameworks typically producing smoother project execution than regions requiring custom analysis for each installation. The regulatory maturation continues as more jurisdictions develop experience with the technology and establish clear compliance pathways. The integration of earth tubes with residential basement spaces produces opportunities for combined heating, cooling, and moisture management benefits that suit specific building configurations. Air handler units located in basements can draw conditioning air through earth tube systems to deliver preconditioned ventilation to living spaces above. The basement integration simplifies installation routing while providing convenient mechanical space for fans, filters, and controls. The approach particularly suits homes with walkout or daylight basements where the earth tube exit points can be integrated with building mechanical spaces efficiently. Consider what earth tube technology means for buildings with appropriate site conditions pursuing maximum ventilation efficiency. The substantial ventilation energy savings of 25 to 45% reduce operating costs meaningfully across extended lifespans. The comfort benefits from gentle, continuous conditioning improve occupant satisfaction measurably. The passive operation without mechanical complexity provides reliable performance without maintenance attention that mechanical systems require. The integration with passive house and high-performance construction supports stringent energy performance targets. The commercial applications extend benefits beyond residential contexts. The climate. Adaptability supports applications from cold continental climates to hot tropical contexts. The educational infrastructure supports knowledgeable design and installation. The question isn't whether earth tubes deserve consideration for appropriate sites committed to high-performance construction. The question is why the technology remains relatively obscure in American construction despite its demonstrated success in European and Asian contexts. The answers involve unfamiliarity, specialized design requirements, and site limitations rather than fundamental limitations of the approach. For projects with adequate site conditions and commitments to comprehensive sustainable building, earth tubes offer distinctive capabilities that conventional mechanical systems cannot match.